Hello, everyone. We are here with the first problem in our 5-1 problem set. It says, a child sitting 1.2 meters from the center of a merry-go-round moves with a speed of 1.10 meters per second. It asks us first to calculate the centripetal acceleration of the child and then to calculate the net horizontal force exerted on the child. Let's focus on A first. We'll need to recall that centripetal acceleration is found by squaring the velocity of an object that is experiencing uniform circular motion and dividing it by the radius of that circular path. All right, so just to give you a quick visualization of what's going on here, there's a kid that is experiencing some uniform circular path around on a merry-go-round, and they are exactly, or said to be, 1.2 meters from the center of that merry-go-round. So if I say the radius of this, if I label the radius of this circle, it'll have to be with 1.20 meters. At the same time, if we say that that child is sitting at this point, then they must have some velocity vector that is tangential to the circular path. So this arrow that I just drew should have a magnitude of 1.10 meters per second. Now, we should notice that that's all that we need in order to find the centripetal acceleration. We have velocity and we have the radius of the circular path. So I'm going to go ahead and just take that and plug that into my formula for centripetal acceleration. So if I plug that 1.10 meters per second in and square it, I'm going to put that over 1.20 meters for my radius. All right. So really quickly, if I pop that into the calculator, then I should get about 1.21. So we can say that that's a 1.21, and meters per second, when we square the whole unit of meters per second, we get meters squared per second squared. I'm going to put that over 1.20 meters, and I'm going to pop that into the calculator to see what I get there. Notice that one of the meters is going to cancel out the second order meter in my numerator, so we're just going to be left with meters per second squared, which is a good indicator that we've solved correctly for acceleration, because that is the SI unit for acceleration. Now, when I take 1.21 and divide it by 1.20, I get to three significant figures, 1.01 meters per second squared. So we're going to say that that is our centripetal acceleration, and that is going to be the acceleration experienced by the child on the merry-go-round. Now, the next step is to find the horizontal net force. Now, in this situation, in this uniform circular motion, the only force acting on the child should be the centripetal force. That said, we can say that our net horizontal force must be equal to the centripetal force that the child is experiencing at any moment on their circular path. So if that's true, then we can just set up Newton's second law and say that as long as we're considering centripetal acceleration, then multiplying that by the mass of our object should give us centripetal force. All right, so F equals ma here, as long as that A is centripetal and as long as that F is also centripetal. From here, we just go ahead and multiply our 1.01 meters per second squared times the mass of the child, and you're ready to go. Good luck. I'll see you in the next one. Here we are with problem 2 in our 5-1 practice set. It says a jet plane traveling at 1,890 kilometers per hour or 525 meters per second pulls out of a dive by moving in an arc of radius 5.2 kilometers. What is the plane's acceleration? All right, so if we're looking for acceleration in some circular path, then we're probably looking for centripetal acceleration. That is given by A sub r is equal to v squared over r, where v squared is the magnitude of the object's velocity, which is given to us, and the radius of the circular motion it's following. If the arc has a radius of 5.2 kilometers, that's the radius we're going to use here for centripetal acceleration. One little issue that I see is that it didn't give us the radius in SI units of meters, so we're going to have to quickly convert that. Now, I'm not going to set up the dimensional analysis because we should remember that kilometers is just 3 orders of magnitude greater than meters, so we can just move that decimal over 3 times. That said, we know that our radius is going to be 5,200 meters and that our velocity is going to be equal to 525 meters per second. I'm going to go ahead and use these two values to plug straight into my formula for centripetal acceleration. That's going to give me 525 meters per second all squared over 5,200 meters. All right, so taking a look at these units, I know that my units on my numerator are going to be meters squared per second squared, and when I divide by meters, that's going to leave me with meters per second squared. So if I just take my 525 squared and I divide it by 5,200, that should go ahead and leave me with about 53 meters per second squared. Okay, and then that should be my centripetal acceleration, but the question is asking me to convert it to acceleration in G's. And the way that we convert to acceleration in G's is we just take how many multiples of acceleration due to gravity can fit into 53 meters per second squared. So from here, we just divide by 9.8 meters per second squared to get G's. If we go ahead and pop that into the calculator, we'll have 5.4 G's. Good luck, guys. I'll see you in the next one. This is the third assigned problem in 5-1 practice, and what it says is, what is the magnitude of the acceleration of a speck of clay on the edge of a potter's wheel turning at 45 RPM, or revolutions per minute, if the wheel's diameter is 35 centimeters? All right, so my first step here is I'm going to decide what we're looking for here. We're looking for acceleration, and I know that we're dealing with circular motion, so I'm going to pop in my formula for finding centripetal acceleration. So that's going to be up here. A sub r is going to be equal to v squared over r. And that v is just the speed of my object as it is moving along its circular path. And r is just the radius of that circular motion. So we don't know exactly the speed, but we can pretty quickly derive the radius because we know that the diameter is, if I say the diameter lowercase d is equal to 35 centimeters, I can pretty quickly convert that to meters just by moving the decimal over twice. So that's going to be 0.35 meters. And with some mental math, I can say that my radius must then be 0.175 meters. That said, I know my radius, but I don't know exactly what my speed is. What is given to me is what we call our frequency. So frequency, typically denoted by lowercase f, it gives me my frequency of 45, and it gives me revolutions per minute. So I'm going to say that that's revs per minute. And I'm going to quickly want to move everything over to SI. So I'm going to go ahead and convert the 45 revolutions per minute to revolutions per second. That's going to be a quick dimensional analysis where I just multiply it by 1 minute over 60 seconds. Pop that in the calculator. That should give you 0.75 revolutions per second, 0.75 revolutions per second. All right, so now I know the frequency in SI, so I don't have to worry about the units there anymore. And what I do know is that this must in some way relate to the speed, or else how else am I going to plug it in to finish my equation here? So the way that we are going to make that connection is we're going to kind of recall the fact that average speed is equal to total distance over time. And so I'm going to use this definition for average speed, and I'm going to say that if we took our total distance to be the circumference of our circular path, and I took my total time as the time that it takes to make one revolution, or the period, then I could remember that the relationship between frequency and period is that like lowercase f is equal to 1 over that period. Okay, so I can go ahead and say, okay, well, if that's equal to t, or if 1 over t is equal to f, then t must be equal to 1 over f. All right, so then I have some relationship here where I have 1 over our frequency. And now we know our frequency. If we can do a little bit of math to find our circumference, then we can find our speed really quickly. So for this, I'm going to plug in 1 over 0.75. And then on top, I'm going to go ahead and have my circumference, which I can pretty quickly deduce because I was given the diameter. So that's just going to be equal to pi times the diameter, or pi times 0.35. I'm going to keep my units in here as much as I can as I'm plugging things in. And so pi times 0.35 over 1 over 0.75. Since I'm using a calculator, I can go ahead and just plug this in and find that whole speed here. So give me a second. That's going to be pi times 0.35. And then I'm going to go ahead and divide that by, in parentheses, 1 over 0.75. That's going to give me a speed of about 0.82 meters per second. All right, so if that's my velocity, then I'm going to go ahead and finally use that value and plug it in to my equation for finding the centripetal acceleration. So I can go ahead and write 0.82 meters per second. This whole thing is going to be squared, and I'm going to then divide it by 0.175 meters. Let's go ahead and pop this into the calculator. And it looks like I'm ending off with about 3.9 meters per second squared. All right. It might be worth running through that one more time, but this would be our final magnitude of acceleration for the speck of clay on the edge of the potter's wheel. Good luck. I'll see you in the next one. Here we are with the fourth problem assigned for 5-1 practice set. It says, how fast in revolutions per minute must a centrifuge rotate if a particle 7 centimeters from the axis of rotation is to experience an acceleration of 125,000 Gs. All right, really quickly, right off the bat, I'm going to convert that Gs, which is a measure of acceleration, to meters per second squared. And to do that, I'm going to go ahead and just multiply it by 9.8. That's going to leave me with an acceleration of 1,225,000. All right, so that must be my centripetal acceleration. That said, I'm also going to write down the fact that I know my radius. That's going to be equal to 0.07 meters. I went ahead and quickly converted 7 centimeters to meters so we can stay in SI. So that said, let me go ahead and write down my units for acceleration, meters per second squared. And from there, we're going to need to find some information about frequency because it's asking us revolutions per minute. And so that would be the definition of frequency here. That said, in order to find that frequency, we're going to need to first find velocity and then find period. And then we just take the inverse of the period to get frequency. All right, that's going to be in revolutions per second. But from there, we can very easily calculate it to revolutions per minute by multiplying by 60. All right, so in order to find that velocity, we're just going to remember the equation for finding centripetal acceleration. So we already know our centripetal acceleration, but I'm going to set up the equation with just variables first so I can solve for v and then plug stuff in. So a sub r, which is my centripetal acceleration, is going to be equal to v squared over r being the radius that I'm dealing with here. That said, I'm going to quickly rearrange this and solve for v. If I multiply both sides by r and then take the square root of both sides, I'll have that v is equal to, let me make that v look a little bit less like an r. I'll have that v is equal to the square root of, wow, what an ugly square root sign, but oh well, r times centripetal acceleration. All right, from here, I'm going to plug in the two values that I already know for a and r and take the square root of them. I'm going to multiply them together and take the square root. All right, so you can probably do that in your calculator really quickly. I'm going to do it really quickly here. I'm going to say that 1,225,000 times 0.07, 85,750 if I take the square root. That should give me about 293 meters per second. All right. So now that I know the velocity that my particle is rotating or is moving at, then I can take our definition of speed and find the period that our particle is experiencing as it is moving in this circular motion. So what I'm saying here is that if I define this as speed, right, it's just the magnitude of velocity in this case, and I say that v is equal to total distance over time, I can make that total distance just the circumference, all right? I can make that total distance just the circumference, and I can divide it by the time it takes to make that single revolution or travel that circumference. So I can make that my period, all right? So if I can really quickly for a second just kind of calculate what my circumference is, which is just 2 pi r, then I can say that that's 2 pi times 0.07 meters. All right, that's going to really quickly give me my circumference. And let me pop that into the calculator really quick. 0.07 times 2 times pi. It'll give me a circumference of about 0.44. And given my velocity, I can now go ahead and take this setup and say that the period must be circumference over my velocity. Make sense, guys? I just multiplied both sides by t and then divided both sides by v so I can isolate t. And from here, I can go ahead and plug in my 0.44, which this should have been in meters. And I can divide it by 293 meters per second. All right. This is going to leave me with a units of seconds. Okay. So 0.44 divided by 293. That's going to leave me with about 0.0015 seconds. If I take those seconds and I just take the inverse of it, then I'm going to have my frequency in revolutions per second. So when I say the inverse of it, I'm saying that t is just equal to 1 over f. All right. So really quickly, if I solve for f, that tells me that f is equal to 1 over t. So all I need to do is take 1 and divide it by my time, 0.015 seconds. So 1 divided by that time should give me a frequency of 666 revs per second. And the thing is that we want it in revolutions per minute. Luckily, that's just going to be a multiple, and we're going to multiply it by 60. So revolutions per minute should give us about 39,970.6 revs per minute. All right, and that's going to be the answer here. There could be some discrepancy based off of how you were rounding as you were calculating. I would recommend that you do your best to keep your calculator going and not shaving off any of those decimals as you move, even if you're kind of writing them down rounded as you go. This would be in scientific notation, should be something close to 3.94 times 10 to the power of 4 revs per minute. Hope this helped. Good luck. I'll see you next time.